We know from a previous video that the equilibrium potential of a given ion is the point at which the chemical gradient is equal and opposite to the electrical gradient. So our chemical gradient, often referred to as the concentration gradient, is equal and opposite to the electrical gradient. So let's take a look at this. Imagine we have a cell, and the cell has a high concentration of sodium on the extracellular side. Draw some big letters out here. And a small concentration of sodium on the inside, and that cell is permeable to sodium. We know that we have a concentration gradient or chemical direction or chemical gradient forcing in that direction into the cell, right? But if I take and I put some positively charged things on the inside of the cell, there will be a electrical gradient pushing in that direction. Now, if we do some sort of vector math and we add these two things together, we end up with a net gradient in that direction, right? And so this would be our net force, or what we refer to as the electrochemical gradient, okay? But what happens if I increase the number of positively charged things on the inside of my cell? As I increase the number of positively charged things on the inside of my cell, this force here will grow, right? And my net force would diminish, go to sort of zero, and I'd end up with no net force. Okay, when that happens, right, we have no net force, we have reached the equilibrium potential of a given ion. So how do we sort of figure that out? Well, what we can do is if we look at a cell and we can do the same thing, right, where we put a whole bunch of sodium on the outside. We put a little amount of sodium on the inside, right? One of the things that we can do is we can use this concentration gradient. If we know what that concentration gradient is, right? We know how much sodium's on the outside. We know how much is on the inside. We can use that to say, okay, we know the concentration gradient. We know the charge of sodium because we know how many valence electrons it gave up, right? And we know what forces are needed, right? And so somebody actually figured this out and figured out the mathematical equation to determine this. So it is called the equilibrium potential of a given ion. And so if we want to know the equilibrium potential of sodium, we can actually calculate that, right? We can use some constants like the universal gas constant. We have to know the temperature of the system because that's going to dictate how the ions move. We have to know the valence of the ion, right? So that's going to tell us the charge. And we can use Faraday's constant. And then we can input the concentration of the ion in the concentration gradient. So we can say the concentration of the ion inside of the cell versus the concentration outside of the cell. And we're going to use the natural log of that. Okay? And so if we do that, that will actually tell us what the equilibrium potential of that ion is. And so it will say, like, the equilibrium potential of sodium is equal to, let's say, 90 millivolts. And I'm making numbers up here. Okay? But if I say that the equilibrium potential of sodium is equal to 90 millivolts, what that means is that the charge in here and the charge out here have to have a difference of 90 millivolts. So if this was, let's say this is 120 millivolts charge in here, and this is 30 millivolts out here, right? My charge in, 120, minus my charge out, 90, means that my electrical gradient pushes in this direction with this magnitude, right? So I can say that I have an electrical gradient of that degree, right? And if it is at 90 millivolts, it means that it is equal and opposite to my concentration gradient that's forcing in that direction. Okay, now let's take a look at this using an example where we need to determine the directional flux of a given ion. So let's say that I have my cell, and let's just use sodium again, since we've been using that one quite frequently. We'll put a high amount on the outside and a low amount on the inside. Okay, and I will tell you that the equilibrium potential of sodium in this instance is, again, let's just use 90 millivolts. Keep things simple. Okay, but in this instance, let's say the charge in is equal to 100 millivolts, and the charge out is equal to 30 millivolts. Okay, so now we have our charge difference is 100 minus 30, which is 70 millivolts. Well, the equilibrium potential of sodium is 90 millivolts. So in order for that to happen, right, in order for the charge difference to be 90 millivolts, right, what do I need to do? I need to put more charge on the inside of the cell. So I need to take this positively charged thing, right, and move it into the cell, right, and bring that charge with it. So as I do that, the charge will increase, and the charge will eventually go up so that the difference across that membrane is 90 millivolts, right? So if we know the charge difference across the cell, and we know the equilibrium potential of a given ion, we can determine the direction of the flux. So let's use one more example of this. So here's my cell membrane, and for this one, let's use potassium, and we're going to put a high amount of potassium on the inside of the cell and a low amount of potassium on the outside of the cell, and we're going to put a membrane for potassium, and we'll say that the equilibrium potential of potassium is equal to negative 80 millivolts. Okay, so what that means is that we need charge out here in the extracellular component to push back in that direction, right? Because it's a negative value now. Okay, so we have to have the charge in, and the charge out has to be a difference of negative 80. So let's say that, let's use the old numbers, right? The charge in is 100 millivolts right now, and the charge out is 30 millivolts. Okay, so the current charge difference across the membrane is equal to 70 millivolts, right? But we have, in an instance, we have the concentration gradient pushing this direction, right? But we need the charge difference to push back in this direction with essentially 80 millivolts of force, but right now it's pushing in this direction, right? With essentially 70 millivolts. So what's going to happen is in order to move this 70 to negative 70, right? I need the difference to reach negative 80. I need to really increase this charge out here. So I'm going to take my positively charged ion, my potassium, and I'm going to move it outside of the cell. I'm going to efflux. And as I do so, this charge here will start to increase and it will go up, right? Which will then decrease that difference, okay? So it will efflux, right? So an ion will flux until the difference across the cell, the voltage difference across the cell, is equal to its equilibrium potential, right? And so one of the things that you have to remember is that the charge difference across the cell is if we take the charge inside of the cell and we subtract the charge outside of the cell, that gives us that charge difference across the cell membrane, right? This is something called the membrane potential. And we're going to talk more about that in a different video, right? But for right now, an ion will move or an ion will flux in a direction such that the membrane potential is equal to its equilibrium potential. So whatever you have to do for moving that ion to move the membrane potential to the equilibrium potential of a given ion, that's what direction that ion will flux.